Hi crew, this is Parfait Masungi here. I'm going to do an example of how to model a panel extension in ABAQUS. And I'm going to use the validated example from this paper that Peter and I had worked on, titled The Post-Buckling Mechanics in Sand or Steel Plate Under Pure Shear, a Focus on Boundary Condition and Load Path. So this is the paper that was published in the Journal of Thin Wall Structures, and the panel extension model. If you scroll down the paper on this page here, on page 3 of the paper, and when I say panel extension, I am referring to this model here, model number D, where my cursor is showing. So that is the panel extension model, and that's what we're going to model today. And the dimensions of the example that we're going to use is also on the paper. I'm going to use this first model here. So the model GT1, that is the model that we're going to use for the paper. So this model here, GT1, G6T1, that is the model that we're going to use. And so here are the geometric parameters of the model. So we have the A, which is the panel aspect ratio, the D, which is the web depth, the thickness of the web, the aspect ratio of the panel, the web slenderness, the thicknesses of the flanges, and then some information about the width of the stiffeners and other informations. And so let's get started. And so the first thing that we need to do is to open up our ABAQUS. And once you open your ABAQUS, you will have a window that looks something like this. And so once you open up your ABAQUS, you have your model. And the first thing that you want to do in ABAQUS is to set your work directory. And so you will come under the file option, select set work directory. And then here, this is where you will select where you want all of your output files to be saved in. Mine is already preset, so mine is under my D drive, and I select this folder here, WSP ABAQUS, and I'll click OK. So that is the folder where all of your jobs and output files will be stored when you run your analysis. And the next thing that you need to do is to save your model file. And so you come again under the file, go to Save As, and then mine, I named it G6T1 AFWFPE tutorial. So that is what I have saved it as. And you will select the folder where you want to save it as similarly, and click OK. I'm going to click to overwrite this. Yes. And then the next thing that we need to do is to rename our model. So I know that this model is G6T1. So under the model tab here, I will click on where it says model. I will right click, and then I'll select rename. And then I will rename my model. I will call this model G6-T1. And since we are doing an eigenvalue analysis in order to determine the elastic critical buckling load, I'm going to add the word VCR buckle in front so that I know what type of analysis I'm doing for this model. And we'll click OK. And so now our model has been renamed. And so now our ABAQUS screen looks like this. Then we are going to create each part. So the first thing that I'm going to create is the web. And so we're going to come here in the tabs and click on the create part here. And then I'm going to rename this web. And since all of these elements are shell elements, we have to select the shell elements. And I'm going to use the extrusion in order for me to create my shell element. You can also use planar if you want to, but I prefer to use the extrusion in order to create my panel extension. And so we click OK. And then we get the screen that looks like this. And so I'm going to create a line that will represent the web depth. And so you can select create lines here. And you can draw a line, a vertical line like this, or you can use coordinate. So when you select this option of create lines, it gives you underneath here where you have your starting point. So I like to use that to create my starting point. So I will select 0, 0. That's my starting point. And since I know my web depth, on the paper, if you see here, this is the paper, and the web depth is 1.27 meters. And so that means that my vertical is going to be my x is going to be 0 and my vertical is going to be 1.27. And so all of the models here will be in meters. And so if you zoom in, you can also select the dimension, add, and then you click on it, and that will tell you that it is 1.27 meters. Click OK. And then we're going to create our extrusion. So our extrusion is the length of our panel extension. And so the full length of the center panel with the panel extension. So we know that this extension here, so we have a center panel and we have a 2 extension in the end. The extension is d/2. So the extension is half of the web. And so in order for us to know the full length of the center panel and the extension, we have to add the depth of the web plus 2 half panel extensions. And so that basically turns out to be twice the depth. And so we know that our aspect ratio of our center panel is 1.79 meters or 1,905 millimeters. And so we have to add 1 depth to that distance. And so it is 1.905 plus 1.27. That gives us 3.175 meters. And so that would be the full longitudinal length of the girder with the panel extension. And so on ABAQUS here, once we have created the line of our web depth, then we will click here to be done with it. And it's going to give us a window to create the extension. And so our extension is 3.175 meters. Click OK. And voila, now you have your web. And the next thing, before we create other elements, we have to create the partitions of the web. Then the partition, that is where the stiffener will be welded to the web. And how we do that, in the same menu here, this is where it says create partition. We will click on that. And we can create partition based on an edge or based on a face. In this case, since I already have a surface, I'm going to use the face. And I'm going to click the sketch here so that I can sketch. Or you can also create datum planes, and you can create partition based on planes. For this example, I'm going to do it based on a sketch. And so once you select the sketch, it's going to tell you to select an edge. And I'm just going to select this edge here. And so now I have my edge. And so what I can do is I can create a line on my edge. And then once I have that line, I can just offset that line. And so we'll select the offset curve, which is this selection here. Click on it and then select my line. And I'm going to click done. And so now it's going to ask me for the offset distance, and I'm going to offset that distance by the length of the extension, which is half of the depth. So our depth is 1.27 meters, and half of that is 0.635. So I'm going to put 0.635 in my box here and click enter. And so now if I zoom out, I see that it created a line on this side, but I want my line to be on this side of the face of the web. And so I will select the flip option and click OK. And then I'm going to use this new line and then offset that by the aspect ratio of the panel. And the aspect ratio of the panel is as you see on the paper, it's the A distance, which is 1.905 meters. And enter, and I see that it created a line here. And I click OK. And then once you click done, and then done again, and now you see you have just created a partition line on the web, and that's where we will weld our stiffness. So now we are done with creating our web, and we'll repeat the same thing to create the flange. And for the flanges, if we go back to the paper, the flanges dimensions are, the width of the flange is 308 millimeters or 0.0308 meters, and then we will use the same longitudinal distances. And so same thing, we're going to come back and create a new part. Select create a new part. We're going to call this flange. And then since we already selected it as a shell element, it's going to keep the same selection for us when we create new elements. And so it's going to be shell. I'm going to keep this the same as extrusion, or you can do a planar if you want to. It's the same, it's the same way to do it. So in this case, I am also going to use extrusion for the flanges. And so I'm going to do extrusion, done. And I'm just going to create a line that represents the width of my flange. And so I'm going to create a line. My origin is 0, 0. And then the width of my flange, as we see in the paper, it is 308 millimeters. In meters, that's 0.308. So since ABAQUS does not use unit, you have to keep track of your units to be consistent in all of your models. Since we're creating this model in metrics using meters, all of my geometric distances also have to be in meters. And so the easiest way to do that is you can just create a line like this and then come and select the dimension, the add dimension menu here, click on it, select your line, and then change the dimension to 0.308. And so the new dimension is going to ask you that it's going to be 0.308, and then enter. And so now we have a horizontal line here. I'm going to erase this and redo this process. So delete, done. And so let's do it all over again. Create lines. I'm going to draw a horizontal line. And then I'm going to select the dimension, click, and then rename this dimension to 0.308, enter. And so now you have to kind of zoom in to see everything. Now I know that my dimension is this 0.038, which is rounded to 0.31 meters. And so you will X out of this, click done, and then it's going to ask you for the depth, which is the full length of the flange, or the full longitudinal length of the flange. And in our case, it is the total length, which is 3.175 meters, which is the sum of the aspect ratio of the center panel plus the length of both extensions. And then now we have our flange. And so after we have our flange, we also have to partition our flange. And so we have to partition the flange where we're going to weld the flange with the web, and where we're going to weld the stiffeners to the flanges. And so same process, we will select the partition here. And then the first one is I'm going to partition the web center line. And so I can select, go back to the edge, and over here where it says edge, you can select the midpoint or datum point if you have any, and then it's going to ask you to select an edge. You can select this edge, and then you can select this midpoint, and then that will create a partition here. But I want to create a partition that goes from this side to the other side. And so the way we do that, I'm going to cancel this. I'm going to come back to the face. And then here on the face, you see where the option where it says use shortest path between 2 points. And so that's what I'm going to use. And then it's asking me to select the starting point, which is I'm going to select the left point here. And then it's asking me to select the end point, which is going to be this other point in the end here. And so let's select that point and click create partition. And now you have created a partition line. And similar to the flanges, I also need to create a partition where I'm going to weld the stiffeners to the flanges. And then same process, I'm going to sketch them. And I'm going to select the sketch partition, select both faces, click done. And then I will select an edge. So I can click on one of the edges. And then same process, I can draw a vertical line here and then offset that vertical line. And so once I've drawn my vertical line here, I'll select the offset option, select both of these lines. So select this line. Let me see. Offset that. So once I've selected my entity and then I click done, and then it's going to ask me the offset distance. My first offset distance is half of the depth, which is 0.635 right there. And then click done. And then I'm also going to offset this line at the same distance, 0.635. Okay. And then I'll need to offset these two lines. So I'm going to select the first one. And I can also hold shift to select both of them at the same time. And then click done. And then I need to offset that one aspect ratio length, which is 1.905 meters. And then it creates it right here. And then click done. And then once everything is done, I can delete these lines that I did not need here. And then I think I have an extra line there. All right. And then click done. Done. And so now we have created our partition and we have created our flange. And so the last thing that we need to create is our stiffener. And so if we go back to the paper, here are the dimensions of the stiffener. So the width of the stiffener is 101.6 millimeters. The depth of the stiffener will be the same depth as the web, so 1.27 meters here. And so that's what we're going to do. And we go back to ABAQUS. We select, create a new part. This part, we're going to call it stiffener. It's a shell element. We're going to select an extrusion, in this case, again, and then we'll click done. And then I'm going to draw a vertical line. And I know that this vertical line needs to be the same depth as the web, which is 1.27. And so I have my stiffener here, and then click done. And then for the depth, that is the width of the stiffeners. And based on the paper says that the width of the stiffener is 101.6 millimeters, but I need to draw that in meters. And so it will be 0.1016 meters. And so here it will be 0.10160 meters. Then done. And then now I have my stiffener element here. And so we do not need to partition the stiffener since it's just a rectangular plate. And so now I've created all my part. And so now we're going to go and assign all the material properties for our parts. And so on the module tab, we're gonna go to properties, select properties. And then since it's we modeling for steel, I'm going to use the same material properties. And so we're gonna click on this option here to create a material property. And it's going to give you a menu that looks like this. And then we're going to call this steel 210 GPa. And so that's just the modulus of elasticity to tells me what material. And so since this we're using metrics, we're going to select the general and we're going to enter the density for a material. So for steel, it's going to be 7850. And so that our density for steel. And this unit here is in Newton per meters cubed. And then we have to select the mechanical option to be able to enter our elastic properties. And so under elasticity, we'll select elastic. And then here we're going to enter the Young's modulus of elasticity. In this case, we're going to enter them in Pascal. So in Pascal, it's going to be 210 e to the power of 9. And then our Poisson ratio is 0.3. And so we enter both of these properties. We have our density and we click OK. So now that we have all of our material properties, now we need to assign the thicknesses of each plate. And so to assign the thicknesses, we will select here the section menu key. So we click section, and then we're going to assign the first thickness of the web. And so we're going to name it web plate. And it's a shell element. It's homogeneous since it's steel. It's all the same material. Click continue. And then under the values, we have to assign the thickness of our element. And so our thickness are also going to be in meters. And on the paper, the thickness of the web, as you see here, is 4.9 millimeters. And we have to enter that into meters. And so in meters, that value is going to be 0.0049 meters. And so that's what we're going to do here. Thickness will be 0.0049, and our material has already been pre-selected. And then the thickness integration point, we can change that, but for this tutorial video, we'll keep it at 5. Okay. And then we also have to create the thicknesses for the flange. And then so repeat the same procedure. We'll call this flange plate. Shell element with homogeneous, okay. And then now the thickness of our flange is based on the paper right here, TF, it's 19.80 millimeters. So 19.80 millimeters in meters, that's going to be 0.0198 meters. And so that's what we're going to enter here, 0.01980 meters. It's already still pre-selected 5 integration points. Okay. And then the last plate is the stiffener. Repeat the same procedure, select stiffener, and then click shell element homogeneous. So this is stiffener plate. Continue. The thickness of our stiffener based on the paper is given right here under the node tab. If you read the node tab, it tells you here that in this study, the stiffener element were all 12.27 meters or 0.5 inches. Since we are modeling in imperial unit, in metrics, we're going to use this value of 12.7 meters, but we have to convert that into meters since our finite element models is in meters. And so 12.7 is converted into 0.0127 meters. And so that's what we're going to put for ABAQUS here, 0.0127 127 meters, and then click OK. And so after all of that has been done, then we are going to go back and now assign each plate with its correct material properties and correct section. And so the first plate that we have here is so in the part menu, you can click this arrow to change between parts. And so we're going to start with the flange. And so how do we assign the sections and material property to all of our parts is with this option here where it says assign section. And so we'll click on the assign section, and it's going to ask us to select the region, and we have to select, click and drag, and just select the whole region, and then click OK, done. And then it's going to give you this menu, and it's going to tell you to choose which section. And in this case, this is the flange. We click on the drop down, we will select flange plate, which we've created a section for it, and we keep everything the same here for the shell offset. Okay, and then it's going to turn into green. Once it turns into green, that means that you have assigned the correct sections. And then on the part, select the next part will be the stiffener. And so same thing, repeat, we're going to assign a section. So click on assign section, and then click select your stiffener, done, and then choose the stiffener option, keep everything the same, and then OK. And then the next will be the web, same thing, assign the section, so click and drag to select the whole web, done. And then here on our drop down, we'll select web plate. And then we see that the material properties is what we have assigned, everything the same. And then click OK. Done. So now when we switch between our parts, everything is green. That means that we've only assigned one section to those plates. And to see if you assign the correct thing, you can click on these elements, which are the managers of the element. So if we click on the section assignment manager, which is this icon here, you'll see that we have assigned this to the flange. And if we change between part, we see that this is stiffener. And if we change to the last part, this is web plate. And so everything is good. So the next thing that we're going to do now is we're going to assemble all of these plates. And so we come back to our module and we click on the assembly menu. And on the assembly menu, it's just going to be blank because we have not assembled anything. And so how we get started with that, we're going to click on this first icon where it says create an instance. So in the assembly, everything that we do here gets saved as an instance. And so we're going to create an instance, and in the instance, we have the parts that we have created. It's good to always click the auto offset so that it's going to offset your parts as you assemble them so you can move them easily. So we're going to select auto offset, and we're going to select all three parts. So first part is the flange, hold the shift key, and then the web. And so we have all of our three parts here, and we're going to click. We can keep this to be dependent on the mesh, and that's something we will do later. And we'll click OK. And so the first thing that I like to do is I like to move all of my parts to the origin. And so we can select this where it says translate instance. We click on that, and I'm going to select both the web and the flange. Done. And then I'm going to move them, select a point, a starting point, and then my end point will be the origin here. And so now I've moved my web and my flange, and then I also need to move my stiffener, which is located somewhere here. And so you can select your stiffener, click done, select a point, starting point, and then you can move it somewhere here, and then done. And so now I have all three parts, the web, the flange, and the stiffener. but I need to have 2 flanges and 4 stiffeners. And the first thing that I need to do is I'm going to first rotate this so that my axis matches the one on the paper. And so if we go back to the paper, if we look on our panel extension, I see that the z-axis is the longitudinal axis, the x-axis is the autoplane axis, and the y-axis is the vertical axis. And so I'm going to rotate my plates on ABAQUS to match these axes, and then we're going to add the parts that we need. And so we see here is that my z-axis is my longitudinal axis on the paper. My z-axis is also my longitudinal, so everything is good there. So based on this, the only thing that I just need to rotate are my stiffeners. And so that's what we're going to do. We're going to select the rotate instance here, icon, click on that, select the element, the part that you want to rotate, click done, and then you can select the y-axis, and then it's going to ask you for the degree of rotation or the angle of rotation. And in this case, the right-hand rule applies. So if you want to rotate it clockwise or counterclockwise, if it's clockwise, it's going to be positive. If it's counterclockwise, if it's clockwise, it's going to be negative. Sorry, and if it's counterclockwise, it's going to be positive. So in this case, I want to rotate it I want to rotate it clockwise, so I'm going to do minus 90 degrees. And so it has rotated, and then I'm going to translate my stiffener from this point to this point, and then click done so that I can see it better. And so the next thing that I need to do, I also need to translate my web. So I'm going to select my web, click done, select the center point of the web and move it to the center point of the flange. And so now I have my web here. And then the last thing that I need to do is take my stiffener, select my stiffener, done. And then I'm going to select the center point of the stiffener here. So this point, click on the point, and then I'm going to select the point of my web here, there, and then click OK. And then I am done. And so now I have one web, one flange, and one stiffener, but I need 2 flanges and 4 stiffeners. So how do we do that? This is where we're going to use this linear pattern in order to populate more parts. And so first I'm going to click on the linear pattern, and then it's going to ask you to select an instance, and then I'm going to select my flange, and then click done. And then it's going to give you this menu here. So this menu gives you the direction and how you want to offset. So in this case, I'm going to use the second dimension, which is the vertical. And so I'm going to reduce this to 1, but here I'm going to keep this to 2 because I need 2 parts. And then the offset distance, I'm just going to do 1.27 meters, which is my web depth. And so click done, and you see that it's previewing that here. And so now I have 2 flanges. And now I'm going to also offset stiffeners. I'm going to click on my part here where linear pattern. So select linear pattern again. I'm going to click on select the stiffener, click done. And then it does this. And so it gives me 1, 2, 3, and 4 stiffeners. And so I can keep this if I want to, which is helpful for me. And so I'm going to click OK. And so now I have 4 stiffeners. And so the rest, we're just going to translate these stiffeners to their correct location. So how we do that, we select the translate instance. I can select both of these stiffeners together. And then I'm going to select the midpoint here, and then move it to this midpoint there. And then OK. And then I also need to select this stiffener here, which is this one, the one in red. Click done, and then select its midpoint here, and then translate it to this midpoint here. and then click OK, and then done. And so now, if you zoom out, I have 2 flanges, I have 1 web, and I have 2 stiffeners on one side, and I have also, if you rotate it, I have stiffeners on this side. And so then we are done with the assembly. So in this menu here, we have assemble. We're done with our assembly. And so that's that for this. If I want to merge all of this assembly into just one part, we can also do that, but we're not going to do that for this tutorial. You can use this merge instance here, and when you click on that, you will, it's asking you to create the part name. So you would call it, let's say, full panel extension with web and flanges and stiffeners, and then select all of the instances and then click OK. And then it's going to create a new part with all of this instance as one part. So cancel here. And so the next thing now, we're going to assign our step in which we're going to run our analysis. And so when I model all of my finite element, what I like to do is I like to always create a static general step as an initial step, because it allows me to go back to run any previous static general step if I need to in the beginning. And so the first thing here we're going to select is we'll create a step. Initially, there's always an initial step in ABAQUS. And I always like to create a static general step before I create my eigenvalue step, where I run my linear elastic buckling analysis. So the first step is going to be static general. So we're going to rename this to static general. And then click on select general, static general, click continue. You leave everything on this menu unchanged. The only thing that we will change here is the nonlinear geometry. Since we will run a linear elastic analysis, we can leave this off and it's not going to make a difference in the result. But since we're going to use this model to also run nonlinear analysis, it's always good to initially turn the nonlinear geometry on. And so we're going to turn on here and then click OK. Now I'm going to create another step, which is my eigenvalue step, where I will run my linear elastic analysis to calculate the elastic critical buckling, shear critical buckling load. So same thing, create a step, and then I'm going to call this eigenvalue. And so this is my eigenvalue step. It's going to come right after the static general step. And then here under the procedure, we're going to select linear perturbation. Click on buckle, and then select the buckle perturbation, and then continue. And then here, the description, we're just going to call it eigenvalue analysis. This is our eigenvalue analysis. And so we can keep the eigensolver as subspace. And then for the number of eigenvalue requested, in this case, we only need to really know the first and second eigenvalues. And so, but I'm going to request for 10 eigenvalues. And then for the number of iterations here, we can leave it at 30. If you have fine mesh or you have more curve advanced shapes, you may need more maximum iteration. Since everything is flat, we can keep this at 30 iteration. Click OK. And so now if we click on our manager, step manager, we see that we have an initial step, which is always there. We have a static general, and we have an eigenvalue buckle analysis with the nonlinear geometry on. And so the next thing is now we will need to assign the interaction. And so on the module, we select the drop down, click interaction. And in interaction here, what that means is just we basically have to weld the flanges to the web and the stiffeners to the webs and the flanges. And so we're going to use what we call tie constraint for our welds. And so how we're going to do that is here on the tab icons, where it says create constraint, you're going to click on that. And it's going to give you a menu that looks like this. And we're just going to create type constraint. And the first constraint that we're creating is the weld. So I'm going to call this weld, web, and flanges. Weld, web, flanges. And so click continue. And so it's asking you now to select a main tab surface. And in this case here, the main tab surface should be the element that is the thicker, that has the largest thickness. In this case, it will be the flanges. But since we're doing a shear study, the most important element for our study is the web. And so I'm going to select my main surface here as the line of my webs. And so we're going to click on surface, and then so now we have to select the regions for the main surface. And the region for our main surface are going to be the lines, these lines here of the webs. So these lines of the web. And so for me to make sure that I'm only selecting the lines of the web, what I can do is I can turn off the view of the flanges on my panel here so that I only select the lines of the webs. And how I do that, on our selection top here where it says view, we can click on the view and then all the way down to where it says assembly display. If you click on the assembly display, it's going to give you a menu that looks like this. I'm going to minimize it just a little bit. And so we have our menu. And so in this menu, we're going to go to instances. And on the instances here, we are going to select the flanges, flanges 1 and the other flanges. And then we're going to click unselect the flanges and then apply. And once you apply, you see that it turns off the flanges, or basically it hides it from my viewer window. And so now I can properly select, hold the shift key and properly select my web lines, which is my main surface. And so once I have those, and then you will click done. And then so now you see, once you click done, you see it's going to ask you below here to now choose the secondary surface. And my secondary surface will be the line of the flanges. And so now I'm also going to click surface. And so now I need to bring back the flanges. So in our instances here, I'm just going to click on the flanges, but I will unselect the web so I can only look at the flanges. Click apply. And then now I can easily just come and select the lines of my flanges. And then click done. And then it's going to ask you to choose which internal surface. Since the thickness of the flanges is the same throughout the length, it doesn't matter whether you select brown or purple. So we'll click brown in this case. And then in this menu here, you do not need to change anything. We'll just click OK. And so if I choose I'll come under my assembly display. Again, I select my web and I click apply. And now I see that my web and my flanges have been welded. And so we're going to repeat the same exercise, but now we need to select the lines of the webs and the flanges to where we're going to weld the stiffeners. So to do that, it's the same exercise. In this case, we're going to click create a constraint. And in this case, it's going to be the weld of the stiffener. So weld stiffener, type constraint, continue. And so it's going to ask you now to choose the main type. And our main type is going to also be a surface type again. And now to select the regions, the main region surface is going to be the surfaces of the flanges and the web in this case. And so I'm going to hide my stiffeners from this view. And so under my assembly display option here, I'm going to unselect the stiffeners and then apply. And then in this case, I'm just going to select these lines where I'm going to weld the stiffeners. And so hold the shift key and just click on these lines. And you have to be a little bit patient with ABAQUS when you're modeling. So click, select this line again, and then also need to select this line. And then if I rotate my object, I'll also select this line. And so now we see that we've selected the lines of the flanges and the web where we're going to weld the stiffeners. And there's one more line that we have here, which is on the opposite side. So we have this line, we have this line vertical, we have both lines of the flanges on both sides, and then same here. And so once we see that, then we'll click done. And then it doesn't matter, since our thickness is the same throughout, we can just select brown. And then now we have to choose the secondary part for our surfaces. And so now in this case, for the secondary parts, we need to select our stiffeners. And so to do that, we're going to click on surface again. And then now in this case, I'm going to select each the stiffeners. So what I can do is I can now select all of my stiffeners under my assembly display option, but unselect my flanges so I can only look at the stiffeners, and click apply. So now I'm only looking at the stiffeners. And so now in this case, we can come and select all of the horizontal first of the stiffeners. So hold the shift key. So I also need to select the verticals. And so, but since I have two stiffeners here, I have to be a little careful so that I can select both of them and not just one of them. And so what I can do is I can turn off the first two stiffeners and then select both verticals, and then bring back the other two stiffeners, but unselect the other ones, apply, and then select the inside of this stiffener. Sorry, so I did not hold the shift key, so now I have to reselect all of my stiffeners. So what I can do is just select like this, hold the shift key, make sure I'm just selecting the edges, and then bring back my other two stiffeners, apply, make sure also hold the shift key when I'm selecting. So if you have to select more than one surface, make sure you hold the shift key. And then now if I bring back all four stiffeners, now I see that I've selected my stiffeners, but I see that I have one line here that I do not need, so I can hold the control key to unselect that. And so if I just check one by one, if I unselect this, apply, so my first stiffener is this, and if I select my second stiffener and I apply, and I see that I need to select the vertical element here, and so hold the shift key, select that, and then if I unselect both, and then I just bring my third stiffener, I apply, and then I see that I only have the edges here, which is good. And then if I select the fourth stiffener, apply, and I see that I only have my edges here. So now everything looks good with all my stiffeners. It looks like I am going to need to correct one more thing here. So unselect this. So let's see. Apply. Unselect all three. That's good. So I need this one is I need to select the inside of it. So the inside of it, which is my stiffener on the opposite side. And so now if I look at it individually, using my manager, apply. I look at the third one, apply. I have this is good. I look at the last one, apply. One is good. I look at the second one, apply. That one is good. First one, apply. That one is good. Second one, apply. That one is good. Third one, apply. It's good. And then fourth one, apply. That one is good. And so if I looked at all of my stiffeners together, I see that I've selected all of the verticals at the line that connects to the web, and then of the horizontal of the line that will connect to the flanges. And then from this, I can bring back all of my elements. So select everything and then apply. And then click done. And then once everything is done, and so now we can X out of my display. And so now we see that we have welded the stiffeners to the webs and the flanges, and the web is welded with the flanges. So now all of our interaction is done. The next thing that we need to do is to assign the boundary conditions and the loads on our model. And so now we'll come on our module menu here, select the drop down, go to loads, and here we have our icons for the loads. So the first thing that we're going to do is create the load. And so we're going to create a shell load, and we're going to load this panel extension under pure shear conditions. And so how we're going to do that is we're going to assign a unit longitudinal load across the web depth on the edges. And so how has that been done on the paper? On the paper here, as you see in this paper, the pink arrows here represent our load. So we're going to assign the load with these directions. And if we go back to ABAQUS, what we're going to do, we have to make sure that our loads are applied on the edges of the web. And so what we're going to do is I'm just going to turn off the flanges so that I can only look at the webs. And so under our view, select the assembly, and then unselect the flanges, and I apply. And then now I'm only looking at the web. And so I'm going to create my load here, select the load icon. And so under the load, for our step, we're going to put the load under the eigenvalue step. That is an important thing to do because we're running an eigenvalue analysis. Our load will have to be in the eigenvalue step. And so we're going to select in shell edge load for the type of the load. We're going to keep everything mechanical and then click continue. And so now it's asking us to select the surface or the edge basically. So we're going to select first the two vertical edges and then click done. And so now for the magnitude of our load, it has to be a transverse shear load first. So for the traction, everything is, the distribution is going to be uniform, but the traction has to be shear. And so we'll select shear. And then the magnitude of our load is 1 kilonewton over the depth of the web. So in our case, 1 kilonewton, which is 1,000 Newton. So in this case, if we take 1,000 and we divide that by the web depth in this case is 1.27 meters, we will get 7.87. And so I'm going to bring a calculator in the screen so we can show you what I'm doing. So we're applying a unit load of 1 kilonewton, which is 1,000 Newton. So if we have 1,000 and we divide that by our web depth, which is 1.27 meters, we have 7.87.4 Newton. And so that is the magnitude of the load that we're going to apply for a shear. And so I can just select this. You can select this whole thing, or you can select up to 4 or 5 or 6 significant digits. In this case, I'm going to just select this whole thing, copy this, and then for my magnitude, just paste it here. And so my magnitude is 7.87. And then click OK. And so when I look here now, the directions, one is going up, one is going down. But in the paper, since we're doing pure shear, we see that the direction of the one on the left side is going up. And so to modify that, we'll select our load manager here, select the load that we've created under the eigenvalue, click edit, and we're going to put a minus sign in front. And so once we put minus here, and at 7.87.402, click OK. And so now we see that the directions have flipped. And then we're going to do the same thing for the longitudinal distance here as well. We're going to apply the same pure shear load. And so now we're going to create a new load, or second load. It's going to be an eigenvalue step. The category is mechanical. The type is shear edge load. And then click continue. And then now we're going to only select the horizontal lines. Click done. And then now our distribution is uniform, but our traction has to be shear. And then the magnitude is going to be 7.87.402, which is what we calculated here by taking 1,000 Newton divided by our web depth. And so click OK. And so now we see that the direction matches. We have up to the left and then down to the right. And so this is the pure shear condition. And so now I have applied my load. The next thing that we need to do is, and now if we go back to the paper, the direction of my loads matches the paper. And so the next thing that we need to do now is to apply what we call the boundary conditions. And these boundary conditions are basically what will define how the plates deform as it buckles. And so as we see here, the U, X, Y, and Z represent the translation, and the UR, URX, URY, and URZ represent the rotation. And so in this paper, we see that we have a condition in the edge here, in both edges, and then we have 4 points conditions on the corners of the webs. And so, these conditions, that's what I'm going to use on my finite element. And so if we go back to our finite element, the first one is this edge condition. And so to apply my boundary conditions, I have to select the icon, the second icon which says create boundary conditions. And then this one, I'm going to call this edge 1. This is my edge 1 conditions. And for my step, I can leave this to be eigenvalue step, but I like to prefer to put it in the initial so that for any future step that I create, my boundary condition will just propagate to all the steps that I create. So we'll select initial for the boundary conditions, and then we'll select displacement and rotation. Keep the same category as mechanical, click continue, and then select only the edge 1 as it is shown in the paper. Hold your shift key and then click done. And so now we get this nice fine menu that tells me U1 represent the X, and then 1 represent the X-axis, 2 represent the Y-axis, and 3 represent the Z-axis as it is given here. And so on the paper, it is shown that edge 1 is restrained. So this panel extension condition is actually free or longitudinally free to translate, but it's prevented to go out of plane, meaning in the X plane. And so we're going to apply those same boundary conditions. So we're going to restrain it out of plane, which is my X U1. And we're going to restrain it to rotate in the X plane and around the Z plane as it is shown in the paper. So it's going to be UR1 and UR3. And then click OK. And so now you see that the orange represents my translation. So this plate cannot translate this way, but it can translate longitudinally in the Z direction. And so it's free to translate longitudinally, and it's restrained from rotation in the X and also in the Z. And the next points are point 2. I'm going to do point 1 first, which is this corner point here. And this corner point here is fully fixed, as we see in the paper. And so we're going to create a new point, call this point 1. Mechanical step is initial, displacement and rotation, continue. Select this point, and then click done. And then on the paper, this point is restrained from all rotation and translation, so that when I start to deform my plate doesn't just fly away continuously. I have to have a point in which it is fixed so it doesn't fly away. Continue. And then the other conditions are the conditions point 2 as shown in the paper. And so it will be create another condition, and this will be point 2. Mechanical category, displacement and rotation, continue. And then I will now select, hold my shift key and select my 3 other points. So 1, 2, and 3. Click done. And then this point is restrained to go out of plane, so which is U1, and it's also restrained against rotation in all 3 axes. So it will be UR1, UR2, and UR3. So these 3 points are not allowed to rotate. The only freedom that we give them is to translate vertically and longitudinally. And we'll click OK. And so now everything is done. And if we click on our manager here, we see that we have an initial step, a static general step, and an eigenvalue step. And our boundary conditions has been propagated. And you can always select all of them and edit if you want to edit any of them. Select, click edit, and then you can reselect or re-edit the conditions. So click OK, X out of this. So now I'm going to bring back my flanges. So from my assembly display option, which I can find in the view here, I'm going to come and reselect my flanges to and select apply. And so now I'll bring back my flanges and click OK. So now I have assigned my boundary conditions. I have assigned my load, my vertical, which is load 1, and my horizontal, which is load 2, and the loading is in pure shear conditions. And I can edit and then we can cancel here. And so we can see the directions of my load and the arrows as they point are correct. I have my boundary condition, everything looks good. Now, the next thing that we need to do from this now is to mesh our part. And so on the module, we'll go to the mesh menu. Here we have the total assembly. In this case, in the object, we're going to select part so we can mesh each part separately. And you can always do a mesh convergence studies, but in this case, we're just going to mesh everything into 1 inches per element. And so we're going to select the icon where it says to seed the part in order to assign the global size of our mesh. And so we click on this and it's going to give us a menu to select the approximate global size of our mesh. And in this case, since I'm doing my model in metrics and I want my finite element global size to be for each quad element to be at least 1 inch. So I have to convert 1 inch into meters. And in this case, 1 inch, we know that 1 inch is 2.54 centimeters. And so in meters, 2.54 centimeters is just 0.0254. And we're going to keep the curvature control on and leave everything the same in this case. And once you click apply, it gives you an idea of the seed of the mesh and how it looks. And we click, if we're happy with that, we can always change this number and make it bigger or smaller. And so if you click OK, and then now we have to mesh our part. And so this is where we select the second icon, mesh part, and then we click yes. And then now we have meshed our part into an approximation of basically 2.54 centimeters. So what that means is that one single square element here is approximately a 2.54 centimeters by 2.54 centimeters, or 1 inch by 1 inch. And so now we can also mesh our stiffener. So we'll select the part to the stiffener. We will repeat the same process. Stiffener, and then so it's going to be 0.0254. Keep the curvature control on, apply, OK, and then create the mesh, yes. And so, and then we also have our flanges, repeat the same process, seed the part, 0.0254, apply, OK, create the mesh, yes. And so before we go on to the next step, we need to assign what type of element we're using. Of course, there's shell elements, but there's also the ABAQUS gives you the possibility to apply different element type. And so in this case, we're going to use, if you read in the paper, it tells you that we use S4 element. And so how do we get to this S4 element, which is really nice for shell element in order to do both linear and nonlinear analysis in terms of strain deformations. So we will select this icon here, which says assign the element type. So you click on the assign element type, and it's going to ask you to select the region. So you click and drag, select all of your region, click done, and then it's going to give you this control menu. And so this is where we select the element type. And so in this element type, in this case, what's pre-selected is this S4R element, which is a node with doubly curved thin or thick shell element with reduced integration for finite membrane strains. In this case, I'm going to unselect the reduced integration in order for me to only have the general purpose shell element for finite membranes and strain. So, and then we click OK, and then done. And then we're going to repeat the same thing for the stiffener. And so assign the type, select my stiffener, done. Unselect the reduced integration in order for me to only have a curved general purpose, a doubly curved general purpose element for finite membrane strains. And then click OK, click done, and then repeat the same thing for the web as well. So assign element type, select all my web parts, click done, and then unselect the reduced integration. And now I only have S4 again, which is a node which has 4 nodes for doubly curved general purpose shell elements. And then click done, and then done. And so now if I click, I'll go away from the part and I click on my assembly here. And now I see that all of my assembly has been meshed and the mesh looks really nice. So don't forget to always save as you go. So Control S, just in case you have a slow machine or ABAQUS crashes. So, and so after we have assigned all of our mesh, then we do not need to do any optimization. In this case, the next step will be to define our job. And so under the module, select the job menu, and then now we have a job. Here is the manager of the job. Here we click to create a job. So what I'm going to do is I'm just going to right click on my model here and then copy that name. And so now we create a job. So create a new job. And then I'm going to call this job VCR buckle G61. And so, and I've got the source is the model. If you have an input file, for example, if you don't have any model, but you have an input file of something, for somebody gave you an input file, you can always also select an input file and just select that specific input file. But in this case, we have a model. We'll select model, VCR buckle, which is our model here, and then click continue. And then the description, you can always call this an eigenvalue analysis, pure shear of panel extension model. And the model is G6-T1. And you can put more things here for the description if you need to. For example, the depth of the plate is equal to 1.27 meters. The thickness of the web is equal to 4.9 millimeters. So you can put TW equal to 4.9 millimeters to give you an idea. And then you can also put like the aspect ratio, or you can put the A, which is 1.905 meters. And so, and then your elasticity, which is equal to 210 GPa. All right. So once that is done, then you click on, we want to run the full analysis, so nothing will change in the submission window. What needs to change, we'll keep the general thing the same, and we have a result output as an ODB file. And then on the memory, so since we want to save a little bit of memory, we're going to reduce the maximum percentage of the analysis memory to 60%. And for our parallelization, we can parallelize this to 4 processors. And so we just increase that number to 4, and then we keep the precision under single precision for the output. And we click OK. So now if we click on your job manager, you have created a job, and you can edit that any way you want to by selecting it and click edit. And you can edit anything that we just did, or you can even rename it. And then the next thing now that we need to do is we have to add something called a node file U in order to be able to properly save our outputs for our linear elastic analysis. So we will come here, so we can X out of this window. Over here in this tab where we have all of these icons, we can click on our model, and then we right click on it, and we're going to select edit keywords, and we're going to edit the keywords of our models. And so it's going to give us a window that looks like this. And here, this is another way for us to also check that we have done everything correctly, because here we see that everything that we've modeled and everything that we have assigned gets saved here in this edit keyword. And so we see that we have a flange, we have that has the shell, it's a shell element. We selected 5 integration point. We know that it's still 210 GPa for the modulus. We have the stiffener, it's also a shell element, and the thickness. And then we have a web, it's also a shell element with a thickness in meters. And then if we scroll all the way down, we have all of our surfaces that we've selected. And now we also see our welds, where we have the first weld, which is the weld of the stiffeners to the flanges and the webs. And we also have the welds of the web and the flanges alone. And then we have our material properties, our density and elasticity and Poisson ratio. We have our boundary condition, which gets saved as a numeric digit by 1, 2, 3 all the way to 6. So 1, 2, 3 are translations, 4, 5, 6 are rotations. And then we have our steps, our eigenvalue steps. And in our eigenvalue step, we selected 10 eigenvalues. And I have our boundary condition in our eigenvalue steps here. And we have our load in our eigenvalue step, which is pure shear, so positive and negative and positive. And then in the end here, we are going to click here and click enter. And then we're going to write star node space file enter u. So this is what we're going to enter here, star node file u, in order for us to correctly save our strain and then our translation results. So we click OK. And that's it. So now we save our model. So the last thing now we need to do is we need to run our analysis. And to run our analysis, we can click on the job manager, select the job that we want to run, and then here where it says submit, we will click the submit in order to run analysis. So I'm going to click it here. I'm going to click submit. And then once we click submit, then it's going to load. And then while it's loading, we wait for our results. And so once you click submit, the current version of ABAQUS 2022 that we have here does not update your status. So you will have to manually monitor the status of your job when you submit it. So the way you do that is you select the job, you can click the monitor file here, and the monitor file that will show you your screen monitor. And so once you click monitor, it gives you this menu here. And then this is where we're going to kind of, we're going to have to keep opening and closing this window. And the eigenvalue analysis is a very short analysis. It takes usually less than 5 minutes to complete. And so if we click on the message file, we see that our analysis is still running. And so we wait until the end, and it's still running. And so we can close out of this and just wait a couple more seconds to monitor it again to see if it has completed. So monitor it again. And then so now on our monitor screen, if we click status, we're still running. And so we wait. And so right now it's on the 8th eigenvalue analysis. We requested 10. So if you remember on your eigenvalue step, we requested 10. So right now it has just converged for the 8th iteration, and now it has to go up to 10. So in a few more seconds, it should be done. And so let's monitor it again. And then so if we scroll all the way down, so now after converging to 8 iteration, we receive an error message which says that we need to increase the number of iteration in order for us to get the requested number of eigenvalues. So what that means is that as it was iterating for the 9th eigenvalue, it did not have enough iteration in order to complete the analysis. And so we're going to have to increase our number of iteration. And so that's an easy thing to do. We just dismiss this, close this window, and we come to our step menu, module, go to step, click on your job manager, select eigenvalue, click edit. And right here where it says maximum number of iteration, we can just take that number, and usually when I do my analysis, I like to increase that to 300 instead of 30. So I just multiply by a factor of 10 and then click OK. And then X out of this and then come back to our job and our menu, and then we can rerun this job here. And so what I'm going to do is I'm just going to copy this job, and then I'm going to delete the old one, and I'm going to rename this one by removing the copy. And then we just rerun this, resubmit this job. And so I click submit. And then it's going to give me this because I already have the same name. I can just choose to overwrite this. Click OK. And so now it will be loading here to submit our job. And so now we just wait until the job is complete in order for us to look at our result. So while we wait, I'm going to bring back the paper so we can look at it and reevaluate what we just did. So this is the paper, and what we just did is a modeling of a panel extension model under pure shear in order to calculate its shear critical elastic load through an eigenvalue analysis. And in order for us to look at the ultimate load, we have to do a nonlinear analysis, and that's a different, similar process of modeling, but different types of analysis. So there's a few changes that we need to make to our model in order for us to do a nonlinear analysis. But in this case, we just focus on the linear first. So in the paper, so the value that we get, this equation here, this V critical here, that is the V critical equation, the theoretical V critical equation based on our flat plate. And so the K represents the shear buckling coefficient, and we have the web area, and then we have 1 minus the Poisson ratio squared times the web slenderness squared. And on the numerator, you have the buckling coefficient pi squared times the Young modulus of elasticity. And so in this paper, we model this panel extension boundary condition. You can also do an exercise to model just the web by itself, which is much simpler. You just have a web, or you can just do web and flanges as well. And these are the conditions and the boundary conditions and the loading. And here are the geometric and material properties. In this case, we just finished modeling this model G61. And here are the geometric conditions. And we have the Young modulus of elasticity for linear analysis. When we go into nonlinear analysis, that's when we need to input the plastic material properties. And so in this paper, we see that the V critical value for this analysis was not reported in this paper here, but since this paper mainly focused on post-buckling, we only reported the ultimate capacity here. And so now we can go back to look at the results, I think. And so if we monitor our results on ABAQUS, and so under the message file, we see that it was able to continue the convergence of the analysis, and it looks like it's still running. And so we're gonna have to hold on for a little bit. So we monitor it again to see the progress. So right here, so we see that now the last number of eigenvalue has converged into the 10th iteration. And then if we see a message here that our analysis has been completed. And if you go on the status file, it will tell us whether or not our analysis was successfully completed. And so status, we see that here, the analysis has completed successfully, which is the message that we want. If you had an error message and your analysis did not complete, you will have to come into the message file and look for that message, and then also check out some of the warnings. And so we see in our analysis here, we have no errors, we have no warnings, and we have our data file, we have our message file, which we can track to see if we have any error messages and how to go about solving them and what are those error messages. And then here you also give you a summary in the end of how long it took to complete the job. So this job specifically took 365 or 66 seconds to complete. So it basically, in this case, 366 seconds, that is approximately 6 minutes. So this analysis only took us 6 minutes to complete. So very short. And so now we can look at our result. And so we'll click on the job, manager, select the job and click the results. And we wait. for it to load our results. And so on our results here, we see that it tells you, your ODB result file, and then it tells you the step in which. So if we want to see the correct result, in this icon tab here, the first one here, that is just the plot with the undeformed shape. So when you first look at your result, it usually shows you the result with all of your undeformed shape. And then in order for us to see the deformed shape, we have to select the second one, which says to plot the contours of the deformed shape here. So we'll click on that. And so boom. Now we see the deformed shape. And this deformed shape here, the first eigenmode is, it says it's negative 199.23. And so this value here is in kilonewton. So this is a negative eigenmode. But we want to look at, since we loaded up our plate in pure shear, we would look at the first positive eigenvalue. And the first positive eigenvalue, to look at that, we will look for it by changing these arrows, since we requested 10. So if the first eigenmode is negative, the second eigenmode will be positive. And if we click on this arrow here to go to the next eigenmode, we see that we have a positive buckle into the shape of the pure shear condition that we assigned. And it says that the eigenvalue is 199.23. So this eigenvalue here is our elastic shear buckling load. So in this study, the V critical for this panel extension will be 199.23 kilonewton. So, and if we go back to the paper, we can kind of look at the ultimate here. If we look at the ultimate for the panel, for this panel extension specifically, the ultimate VU was 445 kilonewton. We only did a linear elastic analysis. So in order for us to reach this 445, we have to do both a linear and non-linear analysis. And that's another step in the modeling process. But specifically for this study, we just wanted to look at V critical. And so that's it for this tutorial video on how to model a panel extension. And so you can always play around this to look at more eigenmodes and eigenvalues. And then so you start to see that it will start to change the shape as you look at different eigenmodes. And then the V critical increases as you increase the eigenmode. So different modes, different eigenvalues. One is positive, one is negative. In our case, we always look at the first positive, which is a reflection of the worst case buckling mode. So that's it for this study and for this modeling tutorial on how to do a model, a panel extension model under pure shear condition in order to look at the elastic shear critical buckling load.